This is Anders. I'll be presenting the Linear Algebra and Real Analysis R term project with Roman, and I will be showing how to plot functions in 3 dimensions, and there will also be an economic application. So I'll be going over the first part, which just goes over how to plot functions in 3 dimensions. And this can be useful because sometimes we can't exactly picture what's going on, for example, in a function like x times y plus 1 over y. The limit as x and y go to 0 is undefined, and it behaves oddly near the origin, but it can be useful to see that graph in 3 dimensions so you can visualize what is going on. And so I start by loading 2 packages. Plotly is a package for plotting 3D graphics, and the numDeriv for getting the Jacobian matrices of partial derivatives. I start by writing a function that takes coordinates in 2 dimensions, applies a function to retrieve the coordinates in 3 dimensions for the plot that we would like to plot. And it takes 4 arguments: the minimum and maximum x values and y values, the function we would like to plot, and also the level of resolution you would like. The function first makes a grid from the minimum to maximum values for x and y. That's just this expand grid function here. And it just applies the function to each row of that grid. So it'll take an x value, a y value, and it will apply the function to each of those. And it will just return those coordinates. So now if we want to evaluate the function z equals x times y plus 1 over y, as we see here, we can just get the surface for that function. In this case, we're defining y as x subscript 2 and x as x subscript 1. We apply the function getSurface that we saw above, and then we can use Plotly to create a graph. This addMesh part of the function is what is adding the data that we just retrieved using that function. And so here we can see what exactly is going on. If you approach the origin from the x-axis, you can see that you're getting close to 0, but it blows up to infinity if you move along the y-axis. And you can click and drag, so it's a very useful way to see this function in 3 dimensions. Now, if thinking about real analysis, if we want to evaluate whether or not the limit as x and y go to 0 exists, we want to know if for all epsilon greater than 0, there's a delta such that the length of the vector x, if that's within delta, that implies that the function f of x is less than epsilon. So if we pick epsilon equals 1, a pretty large epsilon, we see that no matter how small we set delta, there will always be a vector x that's smaller than delta, so that the function f of x is larger than epsilon. So in this case, here we're setting delta equals 0.0001, a very small delta. We're retrieving the coordinates for that function along the range from negative delta to delta. We're drawing this circle that represents delta, that open ball around the origin. And let's see what happens. If we look at this plot, the green circle represents delta. And we can see that there are points at delta where this function is greater than 1. All the points where the orange is sticking out above the green, those are points where the function is greater than epsilon, even though it's within delta of the origin. So we can see from this graph that the limit does not exist. Another thing we can do is look at partial derivatives. So here's another function very similar to getSurface, get partial derivs. And what this function does is it gets a Jacobian matrix, and it can plot the partial derivatives. So here's the part of the function that gets that Jacobian matrix. and then it uses that slope to calculate the coordinates for where you want to be for any point in 3 dimensions. So as an example, we're going to try plotting x squared plus y squared minus z equals 0, that locus. First, we'll just plot the surface using the getSurface function. And then we're going to generate random points to see if it correctly evaluates the partial derivative. So we set n equals to 6. We generate 6 random points using the runIf function. And that spits out these 6 points where we're going to try to evaluate the partial derivative. We have a for loop here that for each value, each of those 6 points, we're going to apply the function getPartialDerivatives, and we're going to add mesh. Here we're adding that to the plot. So we're going to take those 6 points and add what we calculated as a partial derivative to the plot. And this is the result right here. And we can look at this plot, we can spin it around, and we can see these really are the tangent planes for this function. It lines up perfectly. So it looks like our function is working. And now we're going to talk more about how to use these 3D graphs for an economic application.
In the second part of our term project, we introduce you to the optimization of a linear function under the constraint of a Cobb-Douglas function using Newton's method. After a busy semester as a TA, teaching Math 23A, Joe is looking forward to spending the evening with beer and pizza. His Cobb-Douglas utility function is given by the following expression, where x denotes beer and y denotes pizza. His experience has shown that he has a perfect evening at the utility level of 10. So, just the Cobb-Douglas function has the graph that looks like this, again using the library Plotly. We have beer and pizza on the x and y axis and utility and cost on the z axis, respectively. So we add at z equals 10 the utility level that Joe wants to aim at and get the following orange plane. Since Joe wants to spend his vacation on pricey Tahiti, he wants to spend as little money as possible on reaching his utility level of 10. His cost function he faces is given by this expression, where the price for one beer is $1, the price for a pizza is $2.50. So in the following graph, we then add a green structure in order to visualize this cost function. We see that we will need to take the trace of the Cobb-Douglas function when utility is equal to 10, which is the intersection of the orange plane and the blue Cobb-Douglas function, and project it onto the green plane to see where the price is minimized. So in order to actually find the minimum, we set the Cobb-Douglas utility function to 10 and find the x and y coordinates, where again the orange plane intersects the blue surface, and get this expression. Graphically, this again looks like this. Lastly, we want to get exact numerical values of x and y, so that Joe exactly knows how many pizzas and how many beers he needs to consume in order to be fully happy. We restructure our expressions and get y1 with the help of the constraint, and set x0 and y0 as starting points, namely we take 4.6 and 2.7. We also calculate the derivatives, the partial derivatives of the constraint and cost function. We then plug this in to the algorithm of Newton's method and after one iteration we get the following values, namely he should consume 4.528 beers and 2.71 or 2.72 pizzas in order to meet the utility level of 10 at the lowest possible cost. We make sure that this actually is a optimal point by calculating the ratio of the partial derivatives, namely of the constraint and the cost function, and see that they are proportional, since this value is almost very close to 0. So we see that Joe should consume 4.5 beer and 2.7 pizzas. So thank you very much for listening to our presentation, and have a great day.